High fives.
What?
Greetings and welcome, friends. We are in a new chapter, new zone. We're talking about exploring exponential functions, which we're going to talk about today specifically, and logarithmic functions, which that should be a completely new concept for you, and we'll take a look at that a little bit later, maybe mañana. So today's lesson is called Real Exponents and Exponential Functions. Now, I'm going to start off by considering an equation. All right, so here's an example that I want to graph this. Suppose I have the equation y equals 2 to the xth power. All right, so this is different than y equals x to the second power. Right, y equals x squared would be the graph of a parabola, and y equals 2 to the x, all right, is going to be quite interesting. It's actually a very fast growing function. So let's make a table of values here, actually, just for starters. And I'm going to actually start somewhere down here in the middle. What happens if I plug in 0 for x? What's 2 to the 0th?
0.
1. Right. What if I plug in 1 for x? 2 to the first is 2, okay. 4, I agree. 8, yep, 16, I hear that.
32. 64.
Right, and it appears as though this is just simply doubling, right, from the previous y value. I think you agree. And you might remember some of this stuff from properties of exponents, but what happens if I plug in a negative 1?
Negative 2.
No, 2 to the negative first power. Well, think about what happened from here to here. I doubled it. So to go backwards, I'm dividing by 2. Hank is right. 0.5, or better yet, I'll write that as 1/2, even though they're equivalent. So to the negative second power, divide a half by 2, and I would get a quarter. Right? And notice these are positive values. The negative exponent doesn't make them negative, it just makes them reciprocated. And if I had negative 3, this would be 1/8. And you can see that the 248 in the denominator, 248 right there. Yeah, I appreciate all of you, actually. Just letting you know. Actually, let's just take 10 seconds and think about who we appreciate.
I appreciate Maddie and Hank. Maddie, Hal, Hank, Sweeney.
Wow. Okay. Anyways, so let's graph this. What would this graph look like? Let's take a gander, shall we? Now, first of all right. Here's a question: is this graph ever going to get negative?
Yeah. No, a little bit, tiny bit.
A tiny bit?
No.
Like y values speaking.
Oh, no. Never.
All right. So, I mean, I think you agree this is going to get really big because it's doubling every time. But is this ever going to get negative there?
No.
Right? That's like just... What's it going to be approaching over time?
0. Infinity.
In this direction, what's it approaching?
0.
Yeah, it's going to get closer and closer to 0. Is it ever going to equal 0?
No, never. It's gonna like keep cutting in half and half though, so it's like really close to 0, but never actually going to be 0.
I concur. See, I'm going to count up to 8 here. I hope. I lost count already. I think that should be 8-ish. So when I graph this, let's see, 0, 1. Okay, so right, anything to the 0th power is 1. That makes sense. Over 1 up 2, there we go. Okay, so this looks linear right now. When I plug in 2, I get 4, so that's right there. Notice it's doubled in height, and then the next one would be all the way up at 8, so 1, 2, 3, 4. So it's going to double in height and be up at 8 over there, right? And then when I plugged in negative 1, it was at a half, and then a fourth, and then an eighth, and it's going to get super, super close to 0, but never get there. I kind of missed most of those dots, but that's good enough. I didn't cross nothing. Anyways, I don't know. Sure, I did there. But you know the idea. So actually, what was that called when we had a graph approach a line? This line is an asymptote. So it turns out exponential functions do in fact have a horizontal asymptote. They are asymptotic, right? Pretty great stuff. And so notice here it's doubling every time, and here it's halving every time when you go to the left, so to speak. All right, so let me take a look here real quick. Let me graph 2 to the x. Oh, there we are. Bam. All right, something like. So you end up seeing this graph. Bless you. You are welcome. Welcome. Let's see. All right, there's a medium there, and let's make this graph grid form. Let's make it rectangular. There we are, and I can hide these points. So so you can see that it actually it grows quite quickly. I mean, way off the page there, real fast. And if I smoosh it down, you can see that it's actually, right, I can smoosh it down a bit, but it still just grows so fast that it doesn't take long for it to get off the page. Because remember, it's doubling every time. And then look at what's happening on the left-hand side. If I zoom in here, zoomage, zoomage, zoomage. Here we go. Let's see. I'm going to even, let's see, 0.5. All right. It's approaching 0 rather quickly, right there. And if I zoom over, you can see, oh, yeah, it's just getting there so fast. So this graph has a lot of drastic change in it. Whoa, it's all over the place. That was craziness. And one of the things I want to point out, do you think that this graph grows faster than, say, x squared?
Yes. Yes.
Let's see. Now right here, which graph is steeper?
X squared.
X squared is steeper, right? At the beginning. And then suddenly, right, x squared does cross the graph. All right, you can see here, maybe I can even change the color of this guy here. Display color. I'm thinking orange. I'm always a fan of orange. Naranja, you know what I'm saying? So you can see, oh, so x squared appears to grow faster. But, oh, just you wait. What? Man, 2 to the x was losing for a little bit there, and then like once the nitrous kicked in, the NOS, right? It was just like, and just like takes off to the lead, craziness, and then it's so much so that it's just gonna like take off so far away from. Look at that, like that's just like, psh, it's like x squared. You've got nothing on me, right? So crazy. And we'd see similar relationships if I graph that compared to really any polynomial function, right? So if I make this maybe an x to the third, right? Oh, maybe I'm wrong. I mean, x to the third started off a little slow and then seemed to pick up. Yeah, I don't know, guys. Maybe I was wrong. What do you think?
Probably not.
I mean, I've been wrong before about things. It's definitely happened. Oh boy, this is going to be interesting, guys. It's quite the race. Oh, what's going to happen here? I don't know. It doesn't look hopeful. Let me delete this graph and then regraph it. Oh, no way. 2 to the x still wins. Craziness. So, and it actually won by the time we hit 10. Not bad, not bad. 10 to the third is 1,000. 2 to the 10th is 1,024. So this is at 10. It's 24 units higher than that. So exponential functions are really awesome. They grow super fast. They also, I guess, similarly shrink super fast or approach 0 rather quickly. So all sorts of stuff there. Now notice the title of this lesson. It says real exponents. By real, I'm saying this function, 2 to the x, not only exists for values at, like, say, when I plug in 1, or when I plug in 2, what would it mean if I plugged in a half for the exponent? What's the same as? 2 to the half power. Does anyone remember? What's the half exponent the same as? A square root, right? So that's the square root of 2. Square root of 2 exists. So technically, if I plugged in a half here for my x value, let's zoom in. If I plug in a half somewhere around here, this should equal about the square root of 2, which, by the way, is 1.414. So I could plug in rational numbers. But here I'm claiming not only can you plug in rational numbers, you could plug in irrational ones as well. Any real number is a workable exponent. Okay? So that means you could plug in pi. You could plug in the square root of 7, right? All sorts of crazy things. So let's actually consider that, because I think you guys agree this looks like some sort of a smooth curve going on here, right? Let's.
Yeah.
Oh yeah, I'd say so. So let's see. Let me construct a parallel line and construct. Oh. Slow down, friend. And construct maybe a. Oh, I gotta reselect. Perpendicular line between that and that. Right there. Now, so what I'm claiming is, right, that if I plug in, what's the square root of 2 again? I just told us a moment ago. 1.414. So this x value appears to be around 1.414. So what do you think your estimate would be for the y value when I plug in 1.414?
2.75.
Yeah, 2. Well, I don't know. Maybe I'd say 2.55 or something like that. 2.5-ish, right? Somewhere like that. And actually, I could, interestingly enough, measure the coordinates of this point. And let's see if I can. Oh dear, what did I do? Let's see, what is it? There's that button. Bam. Increase that font size. Oh wow. Yeah. Oh wait. Oh, you know what I did wrong? Represent Hank right there. I was thinking this was 2 and this was 3, so that's where I was getting my number. Hank was correct. It was way closer to 2.75. Yeah. So example of Waddy being wrong, Hank being right. Well done, friend. So yeah, so you can see that, if I wanted to get this close to 1.41, you can see where that would end up landing. So it turns out, good news everyone, exponents can be real. What? Craziness. Right? So let's actually consider that. Let's do a couple problems where we consider the idea of real exponents. So let's simplify the following. Simplify. Bam. Suppose I have the problem. I like this one. 7 to the square root of 2 times, let's say 7 to the square root of 3. All right, so those are irrational exponents, but they're real. They're real. So when I multiply two things of the same base, what's the property of exponents? What do I do with those exponents? Add the exponents, right? Square root of 2 plus the square root of 3. Is that the square root of 5? No, I cannot add the insides of exponents like so. So it turns out like this whole thing would be my exponent, kind of weird looking, and I can't simplify that any, because square root of 2 and square root of 3 are not like radicals, right? I mean, I can't combine there in any way. So, but I just want to point out that the property of exponents applies. It works out. Not bad, not bad. Let's see. Let's try another one. What if I've got 5 to the square root of 2 all to the square root of 10? What property of exponents applies there? Power to a power property. What do I do with those exponents? Multiply. So that's going to be 5 to the root 2 times root 10. So that's the same as 5 to the square root of 20. And you guys might remember some of your abilities of reducing radicals. I could break the square root of 20 into a perfect square. What goes into 20? It's a perfect 4, and it goes in 5 times. See, I'm going to jump down here again. Let's see. So 5 to the square root of 4 is 2. And square root of 5 I can't simplify. So I believe your book actually accepts this answer, but I do want to point something out. So guys, remember this property that we just did a moment ago? Power to a power is equal to the product, right, of the exponents. Here I've got the product of two exponents, so I could actually use that property in reverse and write it as a power to a power. So that's going to be the same as 5 squared all to the square root of 5th, right? And 5 squared is 25 to the root 5. All right. So I just want to point out your book does accept this kind of answer. I'm a fan of actually going the rest of the way. And if I wanted to do something like, say, plug in 25 to the square root of 5 in my calculador. Let's see, let me pull this screen over here. Oh, calculador. How nice. 25 to the, all right, and then I could do second square root of 5, and your calculator will actually give you a decimal approximation of that. All right, so
You have to do that?
no, I just want to point out that they do exist, and that if we were to tie it back to our curve, there's no spaces between this curve, right? It's one continuous curve the whole way. You can plug in any irrational number in there at all. All right. Let's see. Do I have time for this other interesting one? No, I'm going to save that one for later. So, talking about the graphs, okay? Let's talk about these giraffes here, friends. Let's talk about what these look like. So let's consider what an exponential function is. Exponential function. All right, and an exponential function is going to be an equation of the form. Let's see if I can write this quickly. An equation of the form. Ready? I'm going to write this in green. Y equals a times b to the xth power. Okay? And then it's got some stipulations here. It's not just, you can't just willy-nilly plug in whatever you want. Where we've got a cannot equal 0. All right? Because if a was 0, then 0 times whatever this is 0, and y equals 0 is not exponential. Right? That would be a horizontal line. So a cannot equal 0. It turns out b has to be greater than 0 is their preference. Because actually, well, think about it. If I raise a negative number to an even exponent, what happens? What's negative 2 all squared?
4.
Positive 4. Negative 2 all cubed, however,
Negative
is negative 8. So, right, remember that it bounces back and forth between positive and negative for between odd and even exponents. So, if I had a negative value for b and I'm raising it to exponents, it's going to be like bouncing up and down all over, and it wouldn't look very cool at all. So, b is greater than 0, and another fact, b cannot equal 1. All right? And this is true because what happens if I raise 1 to the first power, 1 to the second power, 1 to the 10th power, 1 to the googolth power? It's all 1. 1 to the pith power, 1, right? I like it. So, and that would not be exponential because then this would once again just become a constant function, and that's not very interesting to us. So this is what an exponential function is, specifically in terms of base b is what you might call that. So let's take a look at this graph of mine, all right, that I want us to consider, all right. And what I've got here is the graph of y equals, or f of x equals a times b to the x, and currently a is around 1.04, we'll call that 1-ish. And b is 2.03, so that's 2-ish, right? So this is currently equal to y equals 2 to the x-ish. which is currently what I have that dotted orange line equal to. So let's watch what happens as I change the values of b to being a bigger value. All right? What happens for positive values of x? What happens? For the positive x values, compared to y equals 2 to the x, this is growing even faster, right? So if this is 3-ish, notice when I plug in 1, I'd get 3. When I plug in 2, I'd expect to get, instead of doubling each time, it's actually going to triple each time I move over a unit. So it should cross somewhere around 9-ish, which it does. If I plug in 3, I would triple 9, and it should cross where?
27.
Yeah, all the way up at 27 is where it would end up crossing. Is what would happen there. Let's see. Let me change this graph to a rectangular. There we are. It's not going to let me click on that, is it? Aha! I clicked on it. Take that in your face. Sorry, I got excited there. What happens to the left-hand side, though? What's going on here for values that were negative? Yeah, it shrinks even faster as I go to the left, but it grows even faster as I go to positive values, right? So notice the bigger b becomes, the faster it approaches 0, I guess, becomes asymptotic, all right? So in this case, if b is equal to 6, that means it's going to be multiplying by a factor of 6 every time. So it would go from 6, and when I go over 1, it's going to go up to 36. All right, just so you realize what's going on. That thing is multiplying by a factor of 6. Let's see what happens if I scroll down. Scroll down here. So there's 2 again. Here's a little less than 2. All right, so it's still exponential. It's still doing its thing. Now, a moment ago in our definition, I said that it couldn't equal 1. What do you think would happen when this equals 1? What would this look like? Yeah, it would just actually become a horizontal line. That's exactly right, Jacob. Right? So it's going to be horizontal. What happens in this case when b equals negative?
Go other way.
What? Whoa. Look at that. It's like Gumby arms right there. Isn't that great? I imagine like if there was like some awesome giant drum underneath it, it would just be like boom, 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 boom.
Okay, go harder, go harder.
Go hard, yeah.
Bum, 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 bum. So yeah, so notice when it's less than 1, it flips it like that, right? And I want us to think about why. If I say I had this equal to roughly a half, what do I get when I raise 1/2 to the 0th power? I get 1, just like when you raise anything to the 0th power. What happens when I raise 1/2 to the 1st power? I get a half, all right? What happens when I raise 1/2 to the negative 1st power? I would reciprocate and I'd get 2. So it turns out if this was equal to a half, it would be the mirror image of y equals 2 to the x mirrored over the y-axis. So kind of interesting there. And then earlier I said it can never equal a negative. Actually, that is not 0. That was rounded to 0 because that would not work if that was 0. And yeah, once it's negative, it's just like they don't even graph it. It doesn't even make sense. All right. So as far as our values of b, that's what's going on. It kind of affects the shape of the graph. It affects the multiple as far as how fast it's growing each time. So let's see. Let's see if I can get this around 2-ish again. And let's consider what's going to happen if I change the value of a. Okay? So if a is 1, it's kind of a regular shape. Now what's changing as I slide a? The y-intercept is changing, absolutely. Right? So when a is 4, it looks like it's crossing around 4, right? And a is not meaning it's going to multiply by 4 every time I move over, right? That's what this number means, right? It's doubling in height every time. But what this a is going to do, it's going to multiply the heights all by 4. So this is just 4 times higher than this, okay? So it's not exponential, it's just a multiple of 4 times higher. And in fact, notice that with the value of a, not only is it changing the y-intercept because it's 4 times higher than the previous one, it's also multiplying all these to 4 times higher. So instead of being at a half, it's now at 2 because a half times 4 is 2. Bam. So that's what a does. What do you think is going to happen when a is 0?
It's not going to exist.
Whoa. I don't think I could get it there. But when a equals 0, it actually would just be a horizontal line. It'd be the x-axis.
Try it.
And when it's negative, it flips it vertically, right? Just like a leading coefficient on a parabola flips it upside down, same thing there for what's going on there. So if a is negative, I can flip it upside down. If b is less than 1, I can flip it left to right. All right, so all sorts of cool stuff going on there. So just so you're aware of some sort of general behaviors of these graphs. So if I ask you to graph one of these, it'd be good for you to be aware of kind of some of these relationships with a and b, but you could always graph it using a table of values, not unlike we did at the beginning right here, okay? And that's not that bad. So let's see, where do we go from here? Aha, let's talk about solving exponential equations. And this is the last kind of concept we're looking at. We're going to do maybe 3 quick examples of this. Suppose I have the equation. I guess this is an example, like I said. And I want to solve the equation 7 to the x equals 7 to the 4th. So we've never solved for a variable within an exponent before, so that's new to us. But looking at this, what is your thoughts? What are your thoughts? X should what?
4.
X equals 4. Why do you say that?
Because it's the only thing that's different.
Yeah, it's the only thing that's different between these two. Yeah, it makes sense, and it's hard to describe because it's hopefully a little bit obvious, right? For instance, x could not equal 3 because 7 to the 3rd is not ever going to equal 7 to the 4th. X could not equal 10, right? That's not going to work out. X could not equal a negative number because that's not ever going to equal 4. The only value that makes sense is, oh, x must equal 4, right? I think you guys would agree. And it turns out there's a property that allows us to do that, and that is called the property of equality for exponential functions. Exponential functions. All right, and essentially what it says is the following. It says if you have, let's see, b to the x1 equals b to the x2, then what do you think is true?
E equals x2.
X1 must equal x2. And in fact, this is also true in reverse. I also could have said it as b to the x1 equals b to the x2 if and only if x1 equals x2. So I could start here and then go backwards as well. And logically, it's true both ways. All right, so the idea is if I've got, here's Waddy speak for it, if I've got 2 powers that are equal to each other and their bases are the same, then their exponents must be the same as well. Okay, that's the general idea there. So let's try to apply this to a slightly different solving problem. Solve. Suppose I have 2 to the x equals 16 squared. Now, what's the problem here?
Not the same base.
The bases are not the same. This property is only true if the bases are the same. However, one thing I realize is 2 and 16 are both powers of 2. So I could write these as the same base. I could write this as 2 to the x. And what is 16 the same as? 2 to the what power? 2 to the 4th is 16. Right? You guys agree? Substitute there, right? Because 2 to the 2nd is 4, 2 to the 3rd is 8, 2 to the 4th is 16. And if I've got now this power to a power property over here, 2 to the x is equal to, what do I do with those exponents? Multiply, so that's 2 to the x equals 2 to the 8th, and then using the property of equality for exponential functions, what would my conclusion be? X equals 8. It's got to be. Only way it can happen. All right? Eventually we'll have a math step maybe in between here that would be explained, but actually technically, logically, you could conclude that either way. You don't have to write a step. So I'm not dividing both sides by 2 or anything crazy like that. I'm just looking at that expression or equation and coming to a conclusion based off of what I see. All right? One last example. Here we go. Let's get crazy. You guys, let's get loco in here. Here we are. What if I've got 1/3 all to the 2x plus 1 equals, it's okay, don't worry, it'll be all right, we'll do this together, 9 to the x minus 5th power. Ay caramba, mis dedos de los pies, ay naranjas en la cabeza, right? This stuff is crazy, right? But check this out. Now, I can't set these two things equal to each other because their bases are not currently the same, right? But one thing you might notice about 1/3 and 9, those are both powers of what number?
Oh, the 1.
I could rewrite 1/3 as a power of 3. I could rewrite 9 as a power of 3. So my question is, 3 to what power is a third?
27.
3 to the 27th?
3. -1.
3 to the third is 27.
Yeah.
But 3 to what power is 1/3?
1.
1? 3 to the 1 is 3. 3 to the 1/2 is the square root of 3.
1/3.
2/3.
Ooh, guys, don't know your properties of exponents. Anybody, come on here. All right, let's start with the easy one. What's this one?
27. 2. 3.
3 to the 2nd is equal to 9, right? Equal to 9. And 3 to what is, how do I get a reciprocal?
Divide it.
Root.
Square root of 1. -2.
Square root it.
Oh, you got me.
We got you. We got you there. Yeah.
You are to blame.
So, yeah, 3 to the negative first. Now, both of these are written in terms of the same base, so I'll be able to apply that property in a moment. But first, friends, let's deal with our properties of exponents here. Power to power, I'm going to multiply those. Now, when I do so, recognize that this whole thing is going to have to be multiplied by -1. This whole thing is going to have to be multiplied by 2. All right, a little bit crazy, like I said, a little loco. So this is the same as 3 to the -2x minus 1 equals 3 to the 2x minus 10. And looking at that, what logically makes sense?
Just cancel out the 2 x's. Right?
No.
Do that?
No.
Why?
I've got 3 to something equals 3 to something. What must be true?
It's equal.
It's not the same.
What must be true about this and this?
They're the same.
They have to be the same. So let's do that. So let's say -2x minus 1 must equal 2x minus 10. And now I can solve this normal. I no longer have any crazy exponents. Maybe I'll add 2x to both sides. Maybe I'll add 10 to both sides at the same time. And I'm going to do a flipperoo here. 2x plus 2x is 4x. Let's see. -1 plus 10 is 9. And how do I solve that? Divide by 4. Right? So I'm able to solve this because I was able to rewrite those in terms of the same base. Okay, if I couldn't write those as the same base, we'd have problems, friend. For instance, foreshadowing, all right? What if I had 2 to the x equals 3 to the third? We have no way of rewriting 3 as a power of 2 or 2 as a power of 3. We'd be lost. All right, if that was a 2 down here, bam, problem's easy. But that's going to be a skill that we're going to learn later on in this chapter. So anyways, thanks for watching, friends.
Thanks for having me.
Yes, have a great day. Bye-bye.